All right, so this is the hangout for Glaze Color Effect and Color for what are we? January 5th, 2017, the year of the end of the world. So at this point, the lecture that went up today was starting to dive into some more of the subtleties of the crazier special effects. Some really interesting subjects in there, but most likely, the odds are you haven't gotten to that one yet. With the preceding lectures really being about iron and how big of a deal iron is, how much of an influence it has on everything that we do. Just as a color, as a flux, the different types of reactions you can get, the different types of glazes you can get, all of that. And then the previous lecture where we were talking about really going into this notion of phase separation, which is something historically I've discussed, but don't really go into to any great degree because it's really important, but it's also sort of abstract. And controlling it can be a little bit wild. But so there's a lot of information there. And like I said, I'm up for anything. If you guys want to talk about your own studios, we can talk about those. Or nothing at all. We can talk about movies, except I haven't seen any.
Me neither.
Oh, no?
No.
I'm in the same boat here.
No.
No movies?
So, no.
Oh.
It's I'm having a hard time remembering a couple of things. So one of the things was in terms of phase separation.
Mm-hmm.
If I am like in the borderline of crystals forming, I will likely get phase separation. Is that
well? The more likely place where you're going to get something like phase separation is going to be in the not just in the border region, but that lower region of Stull, where all of the ratios start to blend together. And I'm trying to find that slide. Oh, I didn't use that slide in this presentation. Hold on, let me get it in another one. Because when all of the silica to alumina ratios start blending together, that's when the glaze really sort of loses control of its consistency. Okay, so the glaze literally doesn't know, am I a gloss, am I a matte, and it will make all of these different reactions. So hold on, let me pull up the I'll just go with this. Except I already know that's not what I want, but close enough. Well, I can use this one. So when we are here, okay, so down in this lower region, no, see, actually, that's not. I'll go back to this one. When we're down in this lower region, the compositions just switch so easily back and forth. And when you find a lot of glazes that are known as sort of breaking glazes that will crystallize when they roll over an edge, that sort of thing, that's really taking advantage of that phase separation where it totally looks like a completely different glaze. A lot of that is manipulating the running along with manipulating the chemistry. Now, of course, one of the harder things about that is we're now down in this lower corner of Stull, and we can talk about trying to get glazes that are down there. The good news is that we can make glazes that are down there. We're going to have to bring in something soluble like a soda ash, okay, to get into those lower corners. We can talk about the qualities of that, and as we get into sort of the greater special effect conversations, sometimes you make chemical sacrifices for particular effects. So, it really depends on what you want to do. But again, really what it does is it's overloading the system with different silicon alumina. You're also really bringing up the R2O levels, because you have to remember, in this lower corner, yes, from a UMF perspective, there is 1 mole of flux, but to a certain degree, when you're sort of under the 0.3 alumina level, there's so much flux compared to the glass formers that the fluxes sort of take over. And so when we talk about phase separation, that is an effect that you can get. And this is something, actually, I just got this picture from a friend. Oh no, I want the glazes. Where he sent me this image where he's got a glaze here with a lot of phase separation going on. And what he's doing is he's overloading this glaze with boron. So this is a cone 6 glaze where normally we'd expect it to have about 0.15 boron, more or less. This glaze, if I remember off the top of my head, has something like 0.45 boron fired to cone 6. And what that's doing is that the boron can't find a home in the glass. Okay. So in our glasses, we still have this condition of there are only so many open spots to insert a boron molecule and to insert a fluxing molecule. Because going back to how our fluxes are working, they come in and they break an oxygen to silicon bond, right? And the problem is there's only so many of those. Although there's a ton of silica in a glaze, there is still an absolute finite number of those bonds that you can break. If you overload the system, it can no longer insert itself. And I should say, if you overload the system, you can insert as many boron molecules as you can, but there's still a finite number. And so the remaining boron molecules will do something, and in this case, they'll phase separate, where they will make a relatively stable glass all on their own that's literally living hand in hand with the original glass. And so it's cool for an effect. And again, it comes down to this conversation about durability and the quality of the glaze. But, sort of what a lot of the conversations we can have now is, well, you're aware of durability issues. So, we can talk about doing cool decorative things that may or may not be stable in the greater sense of the word.
Okay. That's our 2 questions, actually. Great.
Yeah, I mean it's really cool as to how we do it. And here I'll pull. Actually, I shouldn't have stopped the screen share. That with the phase separation, that you're just getting these 2 compositions. Sometimes they'll crystallize. Sometimes it'll just be breaking and streaking. But it's still, at the end of the day, just comes down to what way are you overloading the system. Because that's all it is. You're inherently overloading the system. Now, as I talk about, there are some other ways that you can fake it. Specifically, titanium will force crystallization, and this becomes one of those things that, like, when I talk about glazes and I talk about the UMF and all that, and people say, "Oh, well, here's a glaze that's a matte glaze, but it's not in the matte region." 9 times out of 10, I look at that formula and it's got a ton of titanium in it. Well, titanium just naturally will crystallize or phase separate on its own. If you have enough titanium, it'll make a glossy surface look matte. It doesn't mean it's violating the rules of Stahl. It's just that titanium wants to crystallize.
It does that.
Right. That's just what it does. And you'll find, start to look at glazes that are a little bit tweaky, a little bit weird. You'll often find there's some rutile or ilmenite or titanium dioxide thrown in there, sort of just to make it cool. And it's a great effect. It doesn't violate the inherent rules of glazes. It's just a little tweak. The same way with, theoretically, you could say the crystalline glazes are phase separated because, to be clear, which I think, did we have that? Yeah. Okay. So we had that in this lecture too, where what's going on is that, remember, crystalline glazes are existing within the glossy region. Okay, that's what's really odd about them. From a phase perspective, from a compositional perspective, they are glossy glazes. But because zinc in the proper conditions will nucleate and grow crystals, it will make crystals. Now, that doesn't mean that there aren't matte glazes at Cone 04. I'm sorry, there aren't matte glazes with zinc. Like, there is absolutely in here, there is matte zinc glazes, right? And I talk about those back here, that you still get a matte region. It's slightly off. It's not quite 5:1, but it's somewhere between 6:1 and 5:1. But that's, again, a completely different type of crystal. The phase separating is the crystalline glazes, where it's just nucleating these willemite crystals because it happens to have that particular. Oh, I gotta keep clicking on the video and not on the PowerPoint, because it just happens to fall in this phase field. And so, you can totally dope your glazes. That's the funny thing of depending on what you want them to do. Keep it on the exterior. Don't make them food safe, but you can make your glazes go absolutely nuts by pushing to lower silicon alumina levels. And, it's not an easy thing to do chemically, but, you totally can do it. So this is a new version. A guy sent me this version of the spreadsheet, which automatically plots on Stull. It's kind of great.
Oh, yeah, look at that on the right.
I'll share it with you guys. Wait, I wanted Nefsi, Whiting, soda ash, EPK, and Flint. Okay, so we come back to this. So if you go, center. So if we go, let's start with Nefsi and Whiting. So 66% and 33%, right? Okay, so that gives us our 0.3 to 0.7. The problem that we'll face is that you've got an alumina level that bottoms out at 0.3. It just cannot go any lower than that because Nefsi brings in that much alumina.
Mm-hmm.
So it shuts off this whole lower area. Well, there are things that you can do to manipulate that. If you bring in soda ash, right, because it doesn't have any silicon or alumina in it, you can push this down really far. Let's take that to 20. And again, I'm going to bring this back to a 0.3 to 0.7. So just these numbers are all going to go crazy, but understand I'm just balancing out a 0.3 to 0.7. 50, 60, 70, 75. So I brought this back to 0.3 to 0.7. So my flux ratio is theoretic balance. My alumina level is now right through the floor. Went from 0.3 to 0.13. And I could push this even farther. I can make this 40. And then make this 100. Oops. 100, 110, 120. That wasn't 115, 120. Okay. So again, the more soda ash I bring into the glaze, the farther down into this corner that we get. Now, for beginners going through Glazes 1, I would never tell you that you can do this because it does affect greater durability. You have such little amounts of silicon alumina. These glazes are going to go crazy. They're going to melt at a very low temperature. You also now have the added problem of this glaze, when normalized, has 18% soda ash. You're going to deal with a solubility issue. Okay. To a certain degree, actually, the cool thing is that there's so much sodium, you're actually going to saturate the water anyway in your glaze. So it actually makes it so that you can use the soda ash to do something crazy. But now, Chiara, you're going to hit a real problem with trying to go to cone 6, though, because the soda ash could very potentially react with your boron sources and make a borax crystal in the water of your glaze, right? And that's a huge problem because it's a super hard crystal. They're really big, and you really can't get rid of them. But compositionally, this totally works. It's got studio problems, but it can do awesome things because, we're all the way down here. You can add in some clay now and make, add in 10% clay. And look, we can move up the matte line here. 20, 50, right? So now, I've got a 3.44 at 0.18 alumina, a 6.13. And this is pretty cool. Now at the same end, this is sort of, the same thing that we're doing with the fake wood ash glazes. Where the fake wood ash glazes just don't have any alkali metal in them. They're all alkali earth. I mean, even that sort of works. It's a lot of clay. I'll just bring this up just to bring it up. So like where you've got 1.0 alkali earth, right? But, you know, I showed this slide in the talk where you can get a matte fake wood ash glaze because the crystals growing in the rivulets are based on the fact that stability of the glass. 5-to-1 and under, it's still going to precipitate a crystal. But because the total glass content is low and the alkaline earth content is high, it will make rivulets, but then the rivulets will crystallize. And because it's a true matte, they'll also run. It's this crazy reaction where you're sort of taking all of these concepts that we've put together at this point and turned it into this new crazy beast. It's sort of fantastic, and it's something that I really want to play with a lot more in the future. Because talking about making surfaces move and sort of building and you know, using your chemistry to your advantage, like there are freaking cool things we can do at this point. Depending on how detached you want to get from functionality. Yeah, I like it.
Cool.
I don't know if I answered your question or just went on a rant, but.
It's so wonderful information anyway.
Yeah.
Oh, good.
Yeah. The other thing is with the oil spot, which I just finished that list. Can that only be done with iron, or can you use copper to do?
It's an interesting question. Can oil spot be done with anything else? Well, copper is the right question to ask, right? Because copper is the one other material we have that's affected by reduction. And we'll talk about that in the upcoming lectures. But at the end of the day, copper and iron are really the only materials that are actually affected by reduction. I don't think you can.
But this is an oxidation glaze, isn't it?
It is an oxidation glaze, and that's a massively important detail. Now, I know some people will force a reduction on the cooling to try to bring out some colors after all the bubbling is done. But again, sort of going through the process of, you know, what you're trying to do is to force this glaze to bubble. Okay, and in the firing, it is bubbling because the red iron oxide turns to black iron oxide. Excuse me. And if it happens when the glaze is molten, then that does absolutely cause bubbles. Now, again, these aren't pinholes. These are massive bubbles. And this picture is, you know, them sort of unhealed. And those bubbles then get material that nucleates. It causes phase separation on the bubbles. And then the bubbles pop and heal, and you get the spots. I think I'm just still contemplating the copper notion. Copper doesn't go through a vigorous conversion is the problem, where iron naturally goes from red to black at cone 4. And that's really what we're taking advantage of. You know, when copper, you know, going back to the whole copper red conversion, where you go from copper carbonate to copper oxide and body reduction, and then you go from copper oxide to copper metal in glaze reduction. Yeah, it's just not that vigorous. I'd have to think about why. CuO, Fe2O3. I'm not really sure. I mean, the oil spots do have a lot of iron, and iron has, well, it's just releasing one oxygen. It goes from Fe2, no, to Fe2O3 to FeO. So no, it's only giving off one oxygen. Yeah, it's only giving off one oxygen molecule. Copper oxide is giving off one oxygen molecule. But there's a lot of it, you know, that's 6 to 10% iron. Hmm. I mean, the other question I guess I'm sort of thinking is, can you dope an iron spotting effect with some other colorants like copper? Now, I
Oh.
know that cobalt is generally is often added to oil spot glazes to increase the effect. It makes the blacks deeper. Some people say it encourages more crystallization. Up for debate. But I can't think of it. I can't think of doing that with copper. It could be worth trying, but I think we need, this goes to a greater conversation I was having with somebody of something that's really not defined, which I know in this lecture I start to talk about. Was it in this one or is it in the next one? Where I start to talk about iron and manganese as fluxes. Right, that iron and manganese absolutely do become fluxes, and that's amazing. Like this Stull chart is sort of mind blowing, and you can see some cool things. Like here's a manganese crawl glaze. Like that's amazing. So that whole zinc crawling thing. Is it? Is the question then becomes, when we look at all of our colorants, right? All of our colorants, although I've been dismissive of this in the past, where this is where we're going to go over the next few lectures, that all of our colorants are either fluxes or refractory. Oops, that's not what I wanted at all. So this is an upcoming lecture. So we'll talk about this, next week, but basically all of our colors are either alkaline or acidic in the way that they're structured. Well, the alkaline we can quickly associate with the alkaline earth and the alkaline metal, which are our fluxes. So when we break this down, are our materials going to be a flux or a refractory? Now, the most common one we have is chrome. If you put chrome in your glaze, it generally dries it up to a small degree. If you put copper in your glaze, it fluxes it. So it's on the fluxing end of flux versus refractory. The question then becomes, how do we at all compensate for this in Stull? Because we now know with iron and manganese exactly how they function in Stull.
Mm-hmm.
But there also comes a condition of when do we begin to consider them? Because honestly, at sort of under 5% iron or manganese, it's not really worth considering them as part of Stull. But over 5%, it becomes fairly relevant. And we actually see that in the oil spots, because when you look at sort of the generic oil spot analysis, you actually end up with a 0.5 to 0.5 flux ratio. But that's actually not true, right? Because we're not calculating for the iron working as an RO, so it actually brings it back up closer to a 0.3 to 0.7. So it's one of those funny little anomalies that the chemistry seems off, but when we consider iron is an RO and then we account for it, it actually brings it back into balance. The crystalline glazes do the same thing. If we weren't going to account for zinc as an RO, the flux ratios would seem totally out of whack. But when you consider that zinc is an RO, it's a perfect 0.3 to 0.7. So, but there are definitely glazes that are pushing those bounds, sort of going back to the manganese glazes with the fake metallics, that they're definitely pushing the bounds of how the glazes are working. But again, if you consider that this is a 0.8 manganese and a 5-to-1, yeah, you get a manganese matte glaze, which is exactly what the fake bronzes are. You're just crystallizing out manganese crystals, manganese silica crystals, which in a glassy base, which look metallic, which is why, this can run and this can have a shine and this can be crystallized because, yeah, it's a matte glaze. That these trends are exactly the same. You're just screwing around with your flux ratios and overloading the system with manganese. It's, you know, pretty cool at the end of the day.
I remember in the Glaciers one you mentioned you didn't think these were food safe. Would this change your opinion about it, or?
Well, I mean, first of all, there's the consideration of, is manganese toxic or not? The toxicity of manganese is often overstated. People make a lot of assumptions about whether or not manganese is toxic. You know, I'm getting to the point. This happened in my Glazes 1 talk last night of like, you know, there are only certain things that I can say as to whether or not something is safe because I'm not a doctor.
Yeah.
You know, I need to get a doctor that can come in and can say this versus that. And I'm still looking for that person.
But I'm seeing it in what looks like a drinking cup, so I'm like, wow.
Yeah, and that's just a picture I found online of like looking for examples of these glazes.
Yeah, no, they are great.
Right. Well, but no, it's an exterior surface.
It is true. I mean,
it is at lip position.
Yeah.
You know, okay, like, so this glaze, it's 0.8. Oops. 0.8 manganese to basically, you know, with the 0.08 sodium and potassium. Yeah. So I'm not crazy about the flux ratio off the top. Mm-hmm. So it's 0.92 RO. And we know from the work I did with Grant that you don't get this same effect by going to 0.3 to 0.7. Okay, the work I did with Grant was at 0.3 to 0.7, and we got matte glazes. Like, that's what's so cool about this. There are definitely matte glazes coming in through here and gloss in through here, but the quality of the matte is not the same at 0.3 to 0.7 as it is at 0.08 to 0.92. I gotta stop clicking on the video to get that effect. No,
it's a good point. Yeah. It's not nicely balanced if you really think about it.
Right, but you know, I mean, now we're at that point where I can talk with you guys, and you know, and Sarah's making sculpture, so it doesn't matter anyway. But that, you know, what nicely balanced really means, because now we start to get into that. You know, it's sort of that thing of, you know, in Glazes 1, I tell you guys, you know, don't grab the electrical wire because you'll electrocute yourself. Don't ever touch the electric wire, you know. But, you know, now that you guys have some experience, and I can say, well, you can, but you have to be grounded and you have to, you know, do this, that, and the other. So it's the same thing of where we are of no matter how much I say, well, these are the rules of Stull. Well, now I'm telling you, well, yeah, these are the rules of Stull of what you'd expect for high performance. If you want a cool effect, here are the rules of Stull for a cool effect. But understand that, yeah, I mean, is this going to be food safe? No. But, you know, now you know that you can do this at different temperatures. Now that you know how you can do this to different qualities of pushing it farther into the matte or farther into the gloss or any of those types of things. You know, that it's definitely, do I have, okay, Peter, stop texting me. So I can go to Glazy and collect. Oh, wait, no, I want me and collections and did I skip past it? Tamaku fake. Oh, fake metallic. Oops. So you can look at all these formulas of where they're coming in. You know, and there's a lot of different variation on what people are doing from a chemical perspective, you know, to make these glazes work. So, you know, here's cone 04. Let's see if I can pull this one up. No, it's not giving me the, oh, there it is. I don't know what this one is. Oh, it doesn't have a picture. I hate it when I click on something it doesn't have a picture. Now, well, actually, there's the other problem. Derek's not. We've talked about this. If he's not quite accounting for the chemistry, so the flux ratios are off. Well, this is going to be hard to look at. I forgot about that. Let me see. So here's but anyway, so this one had, 15% manganese by weight. And then come back here. So here's a cone 10 that's fairly crystally. Here, let's run this. Let's run the numbers on this one. Give me a second. Let me pull up a new spreadsheet because this one doesn't account for iron. Open. Browse with iron. Okay. So this doesn't have the cool little feature on it, but it's a good spreadsheet. One. Shrink it down a little bit. Stop it. Okay. So looking at that composition, it was just red art 31, 24, 60, and 40. So let's make this red art. All right, it's going to be buried. Gold art, red art. So this was 60. This was 40. Eliminate all of these. And then manganese is all I want. 65% manganese on top of it, right? That's crazy. But manganese on this spreadsheet is actually calculated as a material. Okay, so here's the fun stuff that we get with this glaze. Red art 3124 manganese, and we're at a 6.73 to 1, but the silica and alumina levels are crazy low. 0.94 silica, 1.14 alumina. So now we're in that lower corner of our crazy stull using manganese as our RO flux. Our flux ratio on top of it's pretty out of whack. Again, 0.07 to 0.93. And of that, we're getting 0.77 from manganese. Okay. So it's a totally out of whack recipe, but you can sort of, the resolution on this sucks, but you can see you're getting crystallization and phase separation. And we're not even at a 5 to 1. It's at a 6.7 to 1, but it's all about using manganese and being in that lower corner of stull to get this crazy, crazy recipe. But, all the trends are there. It's just using manganese as an RO. And that's exactly what I did with Grant. When we were coming up with the formulas for our tests. I mean, literally all I did with Grant is we did, the standard Nephi, and we just balanced it. Let's bring this down to 30, 20, 25. So, with Nephi and manganese, there's a 0.3 to 0.7. And shocking enough, we get exactly the same trends that you'd get if you were working with calcium, with whiting. 0.31 alumina because of the Nephi size bringing in alumina, 1.47 silica, 4.76 to 1 silica to alumina ratio. And here, watch what happens. If I do this with whiting, okay, I'm just going to delete the manganese and come in with the whiting. This is 33 and this is 66. You get exactly the same numbers, actually, because the silica and alumina are coming from the Nephi side. It doesn't matter what my RO source is. So again, I can delete this and make this 40, 60. But again, that this glaze was going crazy with the red art and the frit. But, it fits the specs of cone 10. Trying to see if there was anything. Let me look at the list, actually. Yeah, this is what I hate is when you don't get a lot of recipes. But I mean, look at these temperature ranges: cone 10, cone 10, cone 05, 04, 02 to 6, 02, 04, 04, 02, 04. Because again, that the reaction is consistent. And actually, this is sort of profound when we talk about temperature and manipulating temperature and what you can do with sculpture or just generating temperature in general. That a lot of the principles are really universal. And actually, I wish Peter was here tonight because I wanted to talk with him of what he's been working on recently, which is really working with the concepts of Stahl at cone 04, because it all totally works. What you start to run into is material problems of how do you get the sodium, the calcium, and the boron at levels that you need to hit cone 04. But yeah, I mean, here's a cone 6, metallic manganese, cone 10. So this one's got a lot less manganese thrown into a base. Oh, from Pete Pinnell. We can run this one just for shits and giggles and move on. Custer. $80.7. Silica. And the thing is remember, people look at these recipes and they go, well, that's a ton of feldspar and that's sort of disorienting. Well, it's not really a ton of feldspar because they're not counting for the fact that 30% manganese should be normalized into this formula instead of just the color and end. That's what's so crazy about working with the manganese and with the iron this way. Flint, manganese, whiting. This is complicated.
Yeah.
Dolomite.
Many decimals too.
Right? So many decimals. Dolomite. What am I missing? Ball clay. OM4. So what did I say? Flint, 7.1. But here we go. The manganese is 30%. Whiting is why 1.2% whiting? I'd love to know, but I'm not going to ask. 1.8% dolomite, 5.7%. All clay. Right, so it looks crazy, but when it's renormalized, that the feldspar goes down to 63%, which is totally normal for a feldspar. And then, what do we get? Yeah, it's a fake bronze, basically, 0.23 to 0.77, a 0.29 alumina level, and 2.91 silica, 7.5 to 1. Now this, he specifically says it's a luster. So that makes me think it's a lot more in line with this, because actually, what did I say? He was at 0.3. So actually he's down even here farther, but he's somewhere between a fake metallic and, just one of these generic manganese flux glazes. So it's all there. It's just, how you want to manipulate. And I think, to sort of give you the sign off, Kiara, of like, you could do totally amazing things on functional wear with these types of glazes. Just don't put them on food surfaces, use them as accents, use them as exterior glazes. Like, I would love to see this. Like, this is one of those things that like we just discovered one day where I was sitting around staring at the periodic table and I was just like, Grant was working with me and I was just like, let's do this. And he's like, okay. And we did it. And like, now I don't even know what to do with it. It's such like a big, like mind changing, expansive conversation about the nature of glazes. Like, it changes everything, but it doesn't change anything because it still works within the existing system. What was I talking about? Nothing important.
It's cool.
It's very cool. I mean, this is why I love this course, because like this stuff, like, well, there's just not time in Glazes 1, but like this is the wicked cool stuff that that we can talk about. Did we get to talk about temperature manipulation last week? We did. Do you have any more questions?
No, I can't remember. So I had in the test in the midterm.
Oh, don't even.
I thought the bigger the diameter, the more opaque the glaze is on the molecule.
Only on the alkaline metals.
Oh.
Only the alkaline metals. On the alkaline earth, it's actually
It's
the
the
complete
opposite.
reverse.
Oh, I didn't get that. Okay.
Where magnesium is opaque, but barium is transparent.
That's interesting.
Yeah.
I missed that one too.
Oh,
Hmm.
it's okay. I won't hold
I mean,
it.
that's the only reason why we would learn it now.
Right. Yeah, but now you know.
Yeah. Mm. I don't have any more questions, I think.
No? Okay. All right, well, everybody can go to bed. Sarah, did you have any more questions for tonight?
I don't think so. I wondered what scale we talked about in clays, but I couldn't remember what it was. But I suppose I could look it up in my notes.
The scale?
Yeah. I have a scale, but it only goes to 1 point past the decimal. And I wondered if I should have one that goes 2 points past the decimal, because, I got some Christmas money, and what else could I buy?
Well,
but I don't remember what that scale was.
Well, I mean, I'll show you. Actually, I happen to have it right here.
Oh, see? Awesome.
This is the scale I use. It's a Scout Pro. I believe the model number is SP202.
SP202.
I believe so.
Okay.
And this one is great because this has got the hook underneath.
Okay.
So for doing the density measurements for clay, you make a little wire basket and
kerosene?
Well, you could do the kerosene testing if you wanted.
Okay.
But that you would need a vacuum chamber.
Okay.
I mean, if you get a cheap vacuum chamber and a vacuum, that's a wicked thing to do. Oh man, we had great results in my clays class this week from one of my students who's testing stuff. Oh, it was so good. Her tests totally matched density predictions. It was so cool. She was like, this clay sucked, and we looked at the predicted density, and yeah, it totally should suck. And then she's like, and this one was awesome by just changing proportion. I'm like, that's where it should be.
Yay.
I know, dumb things I love.
Nope.
This scale only goes up to like 500 grams, but for
Okay.
testing procedures, or maybe it's 600 grams, it's great. I think I saw this one listed for like $300 at
Okay.
on Amazon.
On Amazon.
Yeah, I mean, let me Amazon. Oh, I thought it was that one. There it is. Oh, it's 200 gram capacity. So it's very low. The more money you spend, the higher capacity it can get.
Okay.
But for testing procedures, that's all that you need. If you're trying to make up bigger glaze batches, yeah, you're going to want a higher capacity scale, but they cost more money. But this does go to 2 significant figures, so it gives you super accurate numbers.
Okay.
But yeah, for the density measurements and for if you want to do kerosene density, like, yeah, it's totally easy to do because it's got the throughput for the basket. And I think you guys saw the stuff about I posted all the old class videos for you.
Yep.
Yeah,
Sweet.
that was awesome. Thank
So
you.
I think in the clays I may have posted how to do density measurement video, but if I didn't, remind me and I'll put it up.
Okay.
But yeah,
Awesome.
that's what I use.
I'm gonna turn this down.
Oh yeah. Oh, sorry.
Oh, I'm good. I got it.
Got it. Well, here's the. There's the URL.
Yay.
There's the model number. Although actually, I don't think that the text chat shows up in the videos. So write it down now.
What if I
Or
take
click,
this?
or you can click the link and then
There we go. Oops. There we go.
Got it.
Screen capture. Yes.
Screen capture.
Thank you.
Cool beans. Alrighty, folks. Well, so getting into next week, we start to talk about the colorants. and all of the awesome things that you can do. We're going to talk about one of my favorite subjects of how stains are really working, because I know like one of the common things is, oh yeah, stains, they're just like stains. They're just, it's a color and you throw it in there, but there's a lot more to stains than all of that. So I really love talking about the stains, because we'll talk about the molecular structure of stains and why some of them work and some don't work, and how they relate to colorants and all that, because it's not literally just colorants thrown together. They've got a particular molecular structure, and then how the encapsulated stains work and all that sort of stuff. It's really fun.
Sweet.
Yeah, so good stuff still coming. And then we'll get, well, we won't get into 04 until the end of next week. So there's a big 04 talk about how messed up 04 is, but it's awesome. I know, but well, I'm, the more I dive into 04, the more I just come to love it based on its chaos. But it's like scattering birds and seeing how they move. There's sort of this wonderful pattern to the chaos. It's great.
Cool.
It's a beautiful image.
Yeah.
Okay, y'all. I will catch you later.
Thank you.
Thank you.
Talk to you next week.
Bye.